go. Okay, thus far we have learned about how to create confidence intervals on our population mean mu when we know what the population variance is, and then we use a value from the z distribution. And when we don't know the population variance, then we use a value from the t distribution. Now, what if we want to do a confidence interval on our population variance that we just don't know? So now we're not talking about the mean, but we're talking about the variance. Well, that's what this lecture is about. First things first, we got to learn about a new distribution. This is called the chi-square distribution. So the best way to, people often call it chi-square, but it is, how would I do this phonetically? K-Y, chi-square, okay? Random variable. This is what the distribution looks like. It is very messy, so I'm not holding you responsible for knowing what the actual equation would look like for the PDF. I am holding you responsible for knowing what the range is. Now, by the way, it's really hard to show these as capitals and lowercase. So these are both supposed to be lowercase chi-squares. They look like X's, but you know how when we do a t distribution, I do this and I make a lowercase t and I say f of t because the random variable is capital T. Remember that? And then if I do a z distribution, I go like this and I use a lowercase z. And I use f of z here because the actual random variable is a big Z, right? Same thing here. Chi-square, it's just a label. You know, I call it W if I want to. So this is a lowercase right here. Lowercase, my initials, lowercase, okay? And this is how you make a chi-square random variable. It will have this term we've seen before, n-1 degrees of freedom. It is not symmetric. It doesn't really have anything in common with the z or the t distribution because it's not symmetric. It doesn't even have the same range. A z and a t both go from negative infinity to positive infinity, but a chi-square only goes from 0 to positive infinity. But that's what it looks like. You might ever have to, I don't know if you will, but let me show you how to do it. In the TI series, you can figure out probabilities, just like with the z and with the t. The chi-square has a CDF function so that you can do some integrating. Again, I'm going to use the letters DF for degrees of freedom. So if I'm interested in computing this probability here, again, this is my RV, random variable. This here is that lowercase chi-square that would be on the chi-square axis. Because it's a continuous distribution, I didn't point that out, but I mean, it certainly is. Look at the range on it. The range on it is, there's no commas there, so it's a continuous distribution. So I can use less than or equal to or less than interchangeably. So if I wanted to do this probability, I can use the chi-square CDF, and I would integrate from the lowest value, because I can only go down to 0 on a chi-square, that's the lowest it can be, up to this value of chi-square that I'm interested in, and then the other parameter or argument is going to be the degrees of freedom. If I wanted to compute the probability that I was between, say, one value on the chi-square distribution here up to, like this, let me show you this. Like this. Suppose that I have, so here's 0 and here's my chi-square distribution and it goes to infinity. If I wanted to go from chi-square 1 up to chi-square 2 and get this area, that's what I'm showing with the purple here. So I could use this chi-square CDF and I would go from this first point x1 chi-square 1 to chi-square 2, and then I have to give it the degrees of freedom. If I'm interested in finding the value on the chi-square axis for which the probability that my chi-square n-1 random variable is bigger than that value equals an area, I'm going to use this inverse chi-square function. Now, this is important. It isn't in the TI. So you've got to program it. So you're going to have to, you will program into your calculator And I'll be demonstrating how to use that today, okay? So normally, for example, we have, if we need the inverse Z, we have the inverse norm. If I need a similar value for the t distribution, I have the inverse t. Now I need the inverse chi-square, and I have a link for that actually in the under the general information section of our Canvas page. It says the TI program for chi-square inverse. So you're definitely going to want to go check that out. Okay, so just like we did with the values for Z and T for those confidence intervals, we're going to have similar ones here. So we're going to have chi-square sub alpha n minus 1 and chi-square sub alpha over 2 n minus 1. And again, the key word here is above. All right, so I'm looking for, if I wanted a value such that the area above it, so I'm going to just draw it right here. My table has a texture on it, so it looks funny when I do this. So this would be the chi-square alpha n minus 1 value that gets me the area above it is alpha. And certainly we know that the area below it would be 1 minus alpha because it is a PDF and the area under the total has to be 1. Let me just get something under here. There we go. Similarly, if I wanted a value on the chi-square axis such that the area above it was a value alpha over 2, that would be alpha over 2 n minus 1. Then the area below it would be 1 minus alpha over 2. And as an example, if I can find this value by using that chi-square inverse that's in my calculator that I programmed in. So let me just show you here. If this is 0.025 right here, and that could be either alpha or alpha over 2, it doesn't matter, it just represents the area. But what we would call that value on the chi-square axis, we would call that chi-square 0.025 comma n minus 1, and in this case it's 19. Those are the degrees of freedom. So we know that this area here is 0.975. I don't really need that for this, but if I want to get this value here, I'm going to get it as follows. It's going to equal my how did I put that in my calculator? I programmed it into my calculator. Let me see what I called it. If I go to program, I called it inverse chi. So it's inverse CHI, and this is programmed into my calculator. Me, Dr. Chatton, programmed into my TI. That's how I'm going to get it. So watch how this inverse chi-square program works. Works pretty easily. I'm going to hit, let me go back. I'm going to hit program. Once I've programmed it in, inverse chi, and then I'm going to hit enter again to get it started. It's going to prompt me. It says area right. That's like area above. Maybe I should have called it area above, but the area above here is 0.025. Then I hit enter. It's going to ask me for the degrees of freedom, which is this 19 right here. And then it'll give me this value. Right here, that will be, it's thinking, there we go. It's 32.8523. So right here is 32.8523. And just to show you that that works, I'll show you how you could use that other function in your calculator. If I integrated from 0 up to this value, I should get 0.975. And if I integrated from this value up to infinity, I should get 0.025. So I'll just do it from the bottom part. So if I went to second function distribution, just to prove to myself that this works, and I scroll down and I find, you're never going to use chi-square PDF, by the way, never, don't go there. CDF, that's the integrating function. And I'm going to say, okay, I want you to integrate from 0, comma, up to 32.8523, close parens. It's going to think about, oh, what don't you like? What happened here? Oh, I didn't give it the degrees of freedom. Sorry, my fault. So I'm going to go from 0 to 32.8523, comma, for 19 degrees of freedom. And see, it gets me 0.9749998, right? So that's 0.975. But what you want, the moral of this slide is that you are supposed to program the inverse chi-square into your calculator. So a little bit of practice here, and I'll just use the calculator function. There's a little bit of practice. Again, this should not be a capital. This should be like a lowercase here. So what I'm looking for here is chi-square 0.025 with 10 degrees of freedom. So I want what that value is, because this area is again 0.025, which means this area is 0.975. And then for the one over here, I want to find the value on the chi-square axis. Now notice that this is 0.975, so the area above is much more, so it's going to be closer to 0. So this is chi-square 0.975, comma 15. And this area here, that is 0.975, which means that this little strip here is 0.025. So I just can do my calculator for each one of these. I'm going to use that inverse chi function. So I'm going to go to program. It's not showing, is it? That's better. Program, inverse chi, hit enter again. Area to the right, 0.025. Degrees of freedom is 10. And that's going to get me 20.4832. You might want to, stop. I would recommend stopping this video and actually programming the thing in and then doing these problems along with me. And that way it will stay in your head a lot better that way. And then if I do the same thing over here, clear it. I'm going to go program. Oh no, come on, let's clear it out. Come on, there we go. Stop. Program, there we go. Inverse chi. Area to the right here is 0.975. So I'm going to expect a smaller number, quite a bit smaller than 20, even though the degrees of freedom are a little bit different. I've got 15 degrees of freedom here. And so now this value is going to be let's see, it ends up being a 6.2621. So you're going to need to know how to get each of these values, one that's going to have like a teensy-weensy bit of probability above. And then we're also going to need to know how to get this one, which has a lot more probability above. Again, all the probability under it is 1. Because we need these formulas for our upper and lower bounds on our confidence interval formulas for population population variance. So here, there we go. So these are the formulas. Suppose I want to get the probability is 1 minus alpha that my lower bound and my upper bound capture the true population variance. All right. And I'm going to have two types of intervals. I'm going to have two-sided and one-sided. The two-sided formulas look like this, and see that they use that chi-square value on the chi-square axis of alpha over 2 and then 1 minus alpha over 2. We might be interested in just a one lower bound or one upper bound. And so the denominators here are only going to have the alpha parameter in it and the alpha over 2 in it as well, or alpha, I'm sorry, chi-square alpha, 1 minus chi-square alpha. What did I want to say about this? Oh, if you wanted to have, suppose you were asked for the confidence interval on sigma, not sigma squared, population standard deviation, not variance, we can just augment this here. So for a two-sided confidence interval, the lower bound would be, we have to just take the square root of L hat, right? Because if I take the square root of both of these sides, that gets me sigma in the middle. So I would do the square root of this formula and the square root of that formula for the two-sided. And for down here, I would do, again, the square root, because if I take the square root of each side, it'll get me the lower bound on the standard deviation. And here I'm going to do the square root of the upper bound. And I believe that's the example. Yeah, that is exactly the example that I'm going to be doing next. So another of your formulas. Here is the example. Suppose we want to do a confidence interval here on the population standard deviation, not the variance. So I have formulas for the variance, but I want it on the standard deviation. So like I said, I'm going to be taking the square root there. So let's see what we've got here. I've got a filling machine. It fills bottles with detergent. Now, the reason is that we care about the variance here, and that's what's saying, compute a 95% two-sided confidence interval on the standard deviation or the variance, is because if I overfill a bottle, I'm going to lose product and waste money. If I underfill a bottle, then people who buy this bottle of detergent, if I'm continuously underfilling a bottle and they notice, they're not going to buy my detergent anymore. It's kind of like when you buy a bag of potato chips and there's not, it seems like everything has settled and that there's nothing in the bag, right? You're not going to buy those chips again sometimes. Oh, maybe it's just me. Okay, so what we want here is a two-sided 95% confidence interval on the standard deviation sigma. So we know that I have a formulas for the confidence interval on the variance here, right here. Those are my formulas. But to get a two-sided interval on this standard deviation, I'm just going to take the square root of each of those sides, each of those values. So here, I'm going to take square root of L hat. So I'm going to take the square root of n minus 1 s squared divided by chi square alpha over 2 n minus 1. So we have to find these values, right? Let's see, what have we got here? A random sample of 20 bottles. So I can see that I have an n of 20. So that takes care of one thing in here. They also told me that the sample variance was 3023, and that's in ounces squared. So I've got S squared. That's good. What else do I need? Oh, the only thing I need now for these formulas is I need chi square alpha over 2. And then for me to get the upper bound, I'm going to need that chi square 1 minus alpha over 2. Hang on 1 second here. S squared. And that'll be chi square 1 minus alpha over 2 and minus 1. So let's write those down. So we need a value from the chi-square distribution of alpha over 2. It's a 95% confidence interval. So that means that my alpha, 1 minus alpha is 0.95. So that means that alpha is 0.05. So now this one will be 0.05 divided by 2, n minus 1. And if I use my inverse norm function, like I did on those previous slides, what I'm going to end up with is that will be, oh, we already did this one. It's a 32.8523. We did this one. No, I keep saying 32.8523. And then the other value that I'm going to need is that chi square 1 minus 0.05 over 2, 20 minus 1. And I'll let you confirm that that's going to be an 8.9065. So now I have all of the information. I'm just going to do my do the plug and chug here. So n minus 1, 20 minus 1, sample variance 0.00023 divided by 32.8523. And that should work out to be, when I take the square root of all of this, it will work out to 4 decimal places to be 0.0115. And then the units on it will be ounces because it is on, it's not on the variance, it's on the population standard deviation sigma. And if I plug these in, I'm going to get 20 minus 1, 0.00023 divided by, and I'm going to use this value here, 8.9065. And if everything goes well and I take the square root of all of that, I will get 0.0 and then 3 2s, and that will also be in ounces. So if I had to report this in a meeting, if I work for this company, I'm going to say based upon the sample data, and I'm right here, of 20 observations, the probability that this interval, 0.0115 ounces up to 0.0222 ounces, the probability that that contains the true standard deviation is 0.95. There is a 0.025 chance that the true standard deviation is about 0.0222, and there is a 0.025 chance probability that it is below this value here. So, all right, on to the next section.